So far, we've built the oscillator, video basics, borders, ball counters, ball motion controls, bricks, ball and play counter, and serve logic on sheet 1, the paddle logic, on-screen display, scoring, and sounds on sheet 2, the start game controls and operational latch on sheet 3, and the flip screen circuit on sheet 4. Today we'll add the coinage and credit circuitry from sheet 3, and yep, we're still using the RevFX schematics today because they were rearranged for better flow. You can find high-res images of the original RevF and the updated RevFX schematics in GitHub. We'll start with the coinage logic. We'll need new 7474s in Fox 8, Henry 8, and Henry 9, a new 7404 in Fox 9, a new 74279 in Jack 8, and a new 7400 in Love 9. We'll also be using the remaining 3 input NAND gates from Jack 9, and we're using the 2 coin switches from our control board. Coin 1 and coin 2 are basically the same circuit, so we only need to go over one. There is a slight difference in that the first 2 stages are clocked by different signals, so if you somehow drop 2 coins at the same time, they'll both be registered. We'll show this later. The inverters act to debounce the switches. Super strange to me that we're tying the inverter outputs to ground and the inverters are chained to match. These switches are break before make, so during the break the state remains fixed, and at make that input drops and the opposite output is pulled low. The inverters then rush to match that state. There are 2 gate delays between forcing the output directly to ground through the switch and turning on the output transistor. This doesn't feel right, but the 7404's totem pole output is designed to handle transients and brief short circuits. We could add current limiting resistors to the feedback lines to reduce power rail current spikes and potential output damage, but it's still working fine after 50 years, so we'll just leave those alone. Anyway, in the resting, normally connected position, the first and second stage latches are force set. The data inputs are driven high, and 64 Victor will be cycling the clocks. The stage 1 and 2 outputs will be high, presenting a low to the third stage. The third stage is clocked by 16 Victor prime, and that low data will flow through, holding the SR latch in the set state. 16 Victor prime will also be cycling the SR latch reset, but the set line takes precedence, so it will remain on. We'll leave S3 open for now. All 3 inputs of this NAND gate must be high to drop the output and raise the coin signal. This is suppressed by the low output from stage 3, so the coin signal remains off. When a coin drops, the NO line falls, presenting a low to the first stage data in and releasing the force set of the first 2 stages. That low is clocked in on the first rise of 64 Victor and steps through stage 2 on the next rise of 64 Victor. On the next rise of 16 Victor, the stage 3 output rises, completing the final NAND criteria for dropping the output and raising the coin signal. When 16 Victor falls, it resets the latch, which raises the NAND output and drops the coin signal. The coin signal is therefore 1/2 16 Victor wide. The circuit sits like this until the coin switch returns to the normally connected position and everything returns to its resting state. An actual coin drop has certain timing, but we can hold our switch as long as we like, and releasing it will return these circuits to the resting state. The circuit description in the manual does have this note about how Henry 8 tests the signals for valid widths, but I haven't seen anything that prevents our manual switch use. We also have these inverted coin lines that fall when a coin is dropped. If you remember the game state video, a drop in either of these signals is required to initially set the operational latch and allow the system to run. We've been using push buttons so far for fake coin drops, and we can finally wire these up. To configure a machine for 2 credits per coin, we close S3, which feeds 4 Victor to the NAND gate. When the standard coin drop conditions are met, the double fall and rise of 4 Victor during the high 16 Victor phase causes the NAND output to drop twice, giving 2 credits. Lastly, I hooked up both coin circuits to the same switch to show how simultaneous coin drops are properly registered by the use of the inverted 64 Victor on the second coin instance. Even though these are hooked to the same coin switch, you can see the coin 1 signal drop when 64 Victor 1 is high, and the coin 2 signal drop when 64 Victor 1 is low. So we're done with that, but it's not too exciting because we have no indication that we drop coins other than the operational latch being set, and we can see the coin pulse on the analyzer. We also have this side circuit which drives the physical coin counter. You probably won't use one, but let's wire it up anyway. On the control board, we also have this coin LED which shows this circuit's output. The wiring is a lot simpler than it looks. Each input from this exclusive OR gate is hooked directly to the normally connected side of each switch. Since they're both normally held low, the XOR output and transistor are off. I'm not sure that they purposefully used an exclusive OR gate here. They could have used an AND gate or a couple of diodes as well. I think it was probably just a convenient spare. You can see the mod on a Rev A board in the Able2 site to add this. Easy2 is not too far, so they shipped the 2 coin signals all the way there and the output all the way back. They just kept this long-ass wiring when the driver was moved near the edge connector. Thanks for that. In other single coin slot machines of that time, the coin counter was simply hooked directly to the coin switch. Anyway, when either coin drops, the associated CSV line rises, turning on Q6, which drives pin T low and ticks the physical counter. CR8 is here to shunt back EMF from whatever's inside that thing. If you're just going to use the coin LED on the control board, you can leave this circuit as is or replace Q6 with a common NPN switching transistor. You wouldn't need the back EMF suppressor diode, and I would switch out R14 with a 1K. We'll add an additional footprint for a TO92 NPN package to our retro board to make this easier. I pulled the physical coin counter from my cabinet and hooked it up. Ticks over just fine. Interesting that this counter has over 25,000 hits. That's over $6,000 American during its operational life cycle, assuming these are all real coin drops. The Breakout cabinet was just over 1K, so perhaps 5,000 gross margin. No clue whether that was good or bad for the industry, but it is interesting. The coin signal feeds the credit counter, so let's wire that up. We'll just need a new 74193 and Love 8. All of the other gates are from chips we've already installed. We'll also need some passives and these 2 SCRs. The counter is held in reset while the operational latch is off, or when the down count reaches 0. Interesting that they labeled these as terminal count up and terminal count down instead of the traditional carry and borrow outs. The up pin is fed by an inverted copy of our coin signal, and the other input here comes from the bonus logic that we'll get to in the next part. The down pin is driven by the start game logic, where 1 credit start is a single pulse, and the other input here is a double pulse created by gating the 2 credit start signal with 8 Victor. From the start game logic, we can see that the start signals assert on the rise of 64 Victor, and de-assert on the rise of the next 32 Victor. The 8 Victor gating therefore properly creates 2 decrement pulses. The only results we need from this circuit is whether we have at least 1 or at least 2 credits to enable starting a 1 or 2 player game. If any of counter outputs B, C, or D is on, we have 2 or more credits, and if output A or the 2 credit line is active, we have at least 1 credit. These drive back to the start game enable logic so we can remove our jumpers and wire these up properly. When there are no credits at the end of a game, we reset the operational latch for safety, and we can hook this up as well. These SCRs light up the start game buttons. This was designed over 50 years ago, and since LEDs were kind of crappy, they used incandescent bulbs. These SCRs drive connector pins 6 and 8 to ground, and the other side of the bulbs are connected to 6.3 volts AC. Since pins 6 and 8 are driven low, we were able to connect LEDs directly to them on the control board, and pull those LEDs to 5 volts DC through current limiting resistors. Note that pins Henry and 7 are just ground and not part of some AC phase. They reserve them for this circuit to somewhat isolate them, but they are connected directly to the ground bus on the board. If you're just using the control board and don't plan to run the retro board in a cabinet, you can either leave all of this as is, or once again save cost by using common NPNs. The footprints are totally different, so we'll add TO92 sites to the retro board to make this easier. The last part of this circuit is this simple carry out to load loop. The preload inputs are pulled high, so the intent is that when the credits hit 15, we stay there. But it doesn't work, and we'll see this in a bit. I hooked this hex display to the counter output, and let's turn it on. Drop a coin. The operational latch is set, the coin counter increments to 1, and the start 1 player game lamp comes on. Drop another coin. The counter increments to 2, and the start 2 player game lamp comes on. Keep dropping coins. We get all the way to 15, and then bam, drops to 10. We've just run into that load anomaly I mentioned. It usually rolls to 10, but I've gotten a 7 or a 12 as well. Now this is not really a big deal. I doubt if anyone would drop that many coins, but the fix is easy. If you remember from the last video, the carry output only drops when the up input is low and the counter is at 15. The counter also only increments on the rise of the up input. This creates a dilemma between the up and load timings. Who wins when they both rise at the same time? The counter ends up at some random value depending on the particulars. To fix this, we simply change the preload value to 14 instead of 15. When the counter is at 15 and another coin is inserted, the up and carry pins drop, loading 14. Since 14 is no longer 15, carry immediately rises, leaving that 14 in latches. When up finally rises, the counter steps from 14 to 15 and we basically stayed put. We will modify our retro board to include this fix since it's just grounding this one pin. I also think it would have been nice to have included the credit count in the on-screen display instead of the player up number. You already know which player is up because their score is flashing. I hooked this up temporarily for fun, and you can see that the on-screen display matches the counter. We could change this on our retro board or add a set of jumpers so you could show either, but I think we'll just leave the display alone and show the credit count in LEDs. Let's close S3, so to speak, to test 2 credits per coin. Each drop now adds 2 credits, and the counter doesn't act up at the top. Everything's working nominally, so let's throw today's work into our retro schematic. Add parts. Add labels. rename everything. And wire it up. Coinage and credits are a bit mundane for us, but super important for revenue generation, so we needed to get these done. In the next final breadboard video, we'll build the last two circuits, the bonus logic and empty wall detector. Thanks for watching.